Welcome back. Now that we've introduced all of the components of reinforcement learning, it's time to introduce the Markov decision process, or MDP. An MDP formally describes the environment for reinforcement learning. Here we're going to be looking at a finite case where we have a finite number of states and actions and where the environment is actually fully observable. That means the current state completely characterizes the entire process. Now, almost all reinforcement learning problems can be formalized as MDPs. In fact, the ones that our engineer colleagues usually deal with, which is the case of moving robots, happens to be a continuous formalism, which we can also deal with under this framework, as well as ones where we have only partial observability, meaning where we only get to observe part of the environment and we might make guesses on what else is happening in the environment. And there's another type of problem, the bandit problem, which deals with things like slot machines that have payoffs, but only one state, which we can also deal with in the Markov decision framework. Now, underlying MDPs is the idea of M, right? This idea of a Markov property. So what exactly is Markov? We captured it already in our pre-lecture, but it's worthwhile reminding ourselves what it is, right? What it means is basically this cornerstone step, which is to say that whatever is going to happen in the future is only going to be predicated on what's happening or what's encoded at the present time step. We can take all of the history from what has happened from the previous time steps all the way back into the first time step and encode it into the current time step. With that in mind, the rest of the history is irrelevant. We can just use the single state to predict what is going to happen in the future. So we can say again that the state is a sufficient statistic of what's going on in the future, and that the environment state is a Markov state, right? We can denote the state of the environment as a superscript E, and that the history that goes from all the time periods before is also Markov, and we encoded it into a certain state. So now we can think about the state transition matrix. The state transition matrix just says how we can get from one state to another. You can think of this as a probability transition matrix that just tells us if we're located in a particular state, let's say state S at time t, okay, so this is just a subscript denoting that we're in a particular state, this state that I've circled at a particular time step, what's the probability of transitioning from that state to a particular new state, let's call this S prime, okay, at the next time step. So we can say the probability of going from state as a source to a state as a destination is just encoded by this matrix, right? So the state transition matrix is encapsulated by this script P matrix, which tells us, for example, what's the transition probability given that we're in state 1 to remain in state 1 at the next time step, or perhaps transitioning to one of any n states outside of 1. And similarly, we would need, in this case, for the transition matrix, one row for each particular state that we might be in. Now, of course, this means that the row of the matrix has to sum to 1, because we're basically describing from a particular state what are all of the states that it can go to. And some of these might be 0. There might not be the possibility of moving from one state to another state. And in this case, the transition probability entry in this ij state would be 0. With this in mind, we can start to define what a Markov chain is. A Markov chain is just basically the case of having many of these random states picked from a sample, meaning a sequence of random states, for example, the one at time step 1, the one at time step 2, going on all the way till time step t, right? So then we can define this Markov process as a tuple, a tuple of states, which is going to have the set of states here. Okay, we're going to call this script S. Okay, and then our transition probability matrix that we've talked about on the last slide, which just again defines from going from a particular source to a particular destination for each of the possible states, right? And this would be encoded into some square matrix, where the square matrix would have the total number of states as n, for example.